Block 10 at the terrace of the 3rd floor. Okay? So now let me introduce our speaker. It's a pleasure to introduce my friend Jerry Bona from the University of Illinois at Chicago to speak about initial boundary value problems, forced oscillations, and sediment transport.
Thank you, Rafael. Well, it's an honor and a pleasure for me to be at IMPA to help celebrate the 50th anniversary of one of the world's most important mathematical centers. All of you who know me know my opinion of IMPA. I always say, and I believe it in my soul, that IMPA is the best place in the world to do mathematics. Whenever I'm in IMPA, I just feel like the mathematics is coming out of the walls, and even I can do mathematics in such an environment. Now, I'm going to talk about some initial boundary value problems. I'm going to talk about some mathematics associated with it, and I'm going to talk about some applications. And so this lecture will wander a little bit. Let me start out with a little sketch of an experiment. The experiment actually drives the mathematics. So what you have there is a side view of a channel, a water channel. It's a channel about the length of from here to the wall, mounted with a piston-type wave maker at the your left-hand side. And the idea behind this experiment was to check how well we could model water waves, surface water waves, with some simple models. And we have the Euler equations or Navier-Stokes. But you'll see later that that's not only is it a little complicated, but it would be prohibitive for the actual application that I have in mind at the end of the lecture. So you're looking for simpler models. There are plenty of simple models around, and the one that we fastened on was Korteweg-de Vries type equation. The reason we fastened on that was because that's the sort of wave motion that you find in the nearshore zone of many large bodies of water. Not right up to the beach, but in the part of the water column that we'll be interested in a little bit later. Okay, so the experiment starts as follows. Everything is at rest. The water is at rest. You turn on the wave maker, and you oscillate it more or less, well, periodically. In fact, you have very good control of the wave maker, and you make waves. So these, you'll recognize what happens. The waves go down the channel in one direction. It's a very easy way of making waves that move in only one direction. If you throw a rock in the middle of the channel, waves go in both directions, and you have to sort those out. And I don't want to get involved in that today. Okay, so the experiment involves taking 4 measurements. You see them there. There's 4 measuring devices hovering over the surface, and those measuring devices pick up the signal as it goes by. So what you're measuring is, let's be careful about this. Here's the bottom of the channel. This is the undisturbed free surface. Here's the wave. Might as well be in blue. And the variable that we're interested in is this one. So this is the point x along the channel. T is proportional to time, and that eta of x and t is a deviation of the free surface from its rest position to point x at time t. That's a very important and easily measurable physical variable. So you can write model equations based on that variable. And there you have one sitting in front of you on the board. The exact model equation, not so interesting at the moment. What is interesting is that what mathematical problem are we concerned with here? And the answer is not an initial value problem. In other words, we're not pretending to, and in fact it's extremely difficult, read that almost impossible, to measure a wave motion in a channel of this length that you've set up at one instant of time. The best you can do is use digital cameras, but the error on that is enormous. So what you do is you make these kind of measurements. And so you're at a fixed point, x naught, in the channel, and you're determining the temporal signal. This is like focusing your eye on one part of the channel and watching the water go up and down. Okay, that's the experiment. And that leads very naturally to an initial boundary value problem, as you see. So the initial data is easy. You don't have to measure it because everything's at rest. And the boundary condition, that f of t, is the first measurement there at the left. So you get an initial boundary value problem. This one is posed in a semi-infinite domain. But on the other hand, if you were doing a numerical scheme involved in that, you would have to cut that off somewhere, and you'd have a 2-point boundary value problem. Now, for these Korteweg-de Vries type equations, over the last 35 years, there's been tens of thousands of papers written, almost all about the initial value problem. Why do we write about the initial value problem? Well, for lots of reasons. It's the easiest one to study. And there's a lot of properties about of the initial value problem that don't apply to the boundary value problem. For example, for the initial value problem, if you ignore that dissipative term that I have there, so set nu equal to 0, there's conservation of energy. The damping is ignored, so the energy is conserved forever. Here, that's manifestly not true. You're starting out with 0, so the energy is 0, and you turn on the wave maker, and you're constantly pumping energy into the system. So there's not conservation of energy. There is, of course, conservation of overall energy, but we're not modeling, we're not doing anything to model what happens close to the wave maker. I'll come to that later. Okay, so that's the problem. Now we'll come back to the experiment in a minute. But let me now shift gears and look at the mathematical issues that are implied. Oh, and I'm naughty as usual. There's a whole list of people the ones in red are just my students. That's, they're not any better than the rest, but I'm proud of them, so I put them in red.
Also, the size of the letter.
The size of the letters is bigger. That's exactly right. You are right. The rest of them are not such bad mathematicians. There are 2 or 3 pretty good ones. Okay, so now I'm going to, as I say, I've shifted gears. I'm thinking as a mathematician at the moment. So let's think about the Korteweg-de Vries equation, which is one of the models that arises here. It's not the only one, but it's one. So the Korteweg-de Vries equation, written so that you don't see any of the nasty physical coefficients, looks like that. Okay, so eta is exactly that variable that I have over there, and that subscripts are partial derivatives, and that's the Korteweg-de Vries equation. Now, and as I said before, what we have been studying for 35 years is the initial value problem. Say posed on the whole real line. But it could be a periodic initial value problem as well. Not much changes at a certain level of thinking. Now, I'm going to review for you very quickly the modern theory for this problem, because it's generated, there's in the last 15-ish years, well, actually 20 if you, the work really started with Cato, although there was precursors, Bob Sachs, for example, which some work that's not so well known, and Amy Cohen, both did something before Cato. But Cato was the first one to really understand some of what I'm about to say. Okay, so how does the modern theory go? Well, the first thing you do in the modern theory is move, well, even a long time ago, you move to a traveling frame of reference to get rid of that term because, well, if you can get rid of a term, why not? So you're now in a traveling frame of reference. You have to keep that in mind. And then you get the equation that looks like that. It's the same equation. It's exactly equivalent. But you're running along beside the channel now at speed, well, 1 in these variables. Okay, so here's this pure initial value problem. By the way, eta became u, and I don't know why. Okay, and there's a list of people who have made major contributions. There's Sachs and Cohen. Major contributions to the subject, and it's still going on. There are papers. I've got preprints sitting on my desk about this initial value problem, and the modern theory is terrifically interesting. Let me tell you how it goes. Well, it's very simple. At one level, you put the nonlinear term on the right, linear stuff on the left. That's what we always do. And then you solve it, pretending you know the right-hand side. You don't, but you pretend you do. And so now it's a linear equation you solve by taking the Fourier transform, and you get a semigroup operating on the initial data phi, and you get a de Hammel type formula with the same semigroup. So this is stuff we actually teach undergraduates, right? Some of them learn it. There's nothing about this semigroup that's abstract. It's very concrete. if you work it out and you find it's the kernel that's involved, it's a convolution, and the kernel is the Airy function. Okay, Sir George Airy. And by the way, let me correct something that, for a few of the experts in the audience, let me correct a misapprehension that many people seem to have. Airy never wrote down that equation. Stokes wrote that down, not Airy. That's not the Airy equation. If you want to call it something, it's the Stokes equation. I'm talking about the linear equation. Okay, a lot of people call that the Airy equation because of this Airy function, but Airy had nothing to say about it. Okay, so the crux of the matter, then, so I've now written U as, if you remember what f is, you've written U in terms of U. And so you're after a fixed point argument, at least for small time. And the problem is immediately obvious. You've got a derivative over here. So you've lost a derivative, so you're not going to be able to balance the function classes. Right? You start with one class, the right-hand side is going to be in a worse function class, and it's not going to work. So it doesn't look like this approach is a very good one. However, if you analyze that double integral, what you find is that there is some very subtle smoothing associated with solving the equation, in particular the smoothing involved in that double integral. And that smoothing brings you home. And so the theory as it currently stands is this. It's globally well posed in the L2 based sobre left classes HS for any s bigger than -3/4. That's pretty amazing. The delta function is in there, right? And so you have to think to yourself, if I have a delta function here, how do I make sense out of that term? I mean, not only is it a product of distributions, but there's a derivative there as well. It doesn't look very, very hopeful. Okay, but it's the smoothing that does it for you. All right, now the initial boundary value problem falls to a similar kind of analysis, although the details are quite different. We'll see. So there's now the problem, and I can't move to a traveling frame of reference, because if I do, the boundary condition I will no longer have a nice quarter plane. I'll have something like that with a moving boundary. The complication induced by that is worse than leaving the UX term, that transport term in, so you leave it in, but it causes trouble. You'll see in a minute. Okay, so there are two problems that are interesting for that for us today. One is that problem in a quarter plane where you think of the channel as unbounded, and the other is a two-point boundary value problem. Okay, and we have things to say. We means Shuming Sun and Bingyu Zhang. We have things to say about both, but I'm going to deal with the first one. Okay, so how do you solve this problem? Well, you do the same thing. You put the nonlinear term on the right, sorry. And now you've got a linear problem in a linear boundary value problem in a quarter plane. Well, you can't use a Fourier transform for that. Even this problem is not simple even as it stands. But if you use the Laplace transform, you can't use the Fourier transform. If you use the Laplace transform, you can represent the solution like this. There's a semigroup. It's now a semigroup, not a group. There's a semigroup operating on F. That's the initial data. There's another semigroup that operates on the boundary data, which is G is equal to H, sorry. And then there's a de Hammel type term, which is involved in this first semigroup. Okay, that's the structure of it. Now, in a little more detail, because it's amusing, how do you get that representation? So let me just run through it quickly. Lambda is the dual variable for the Laplace transform. So it's dual to time. I'm taking a Laplace transform in time, not space. So you take the Laplace transform in time, and you've got a third order ordinary differential equation with the initial data, which is now to become phi instead of f. So you see, I imagine my students get a little bit confused when I lecture, but you guys won't. All right, so there's a third order initial boundary value problem for an ordinary differential equation. By the way, you'll look a long time to find any real theory for third order ordinary differential equations at any level. Second order, fourth order, sure. Third order, very little. Just look at any of your favorite books and you'll see there's very little discussion of it. Okay, but anyway, never mind. You can work it out. This is not very difficult. And so there's a Green's function. which is pretty complicated, but you can write it down. That's against phi, and then there's just the solution of the homogeneous problem. And the R there is a solution of the characteristic equation. Here it is. And you see it would be lovely if it was r cubed plus lambda and not r cubed plus r plus lambda. And what that means is if I could get rid of this a to x term, life would actually be a lot easier. But unfortunately, you can't. That's not the physically relevant problem. So you're left with solving this in cubic, which you can do, but it's easy to go wrong. And then you take the inverse Laplace transform. Okay? So remember how that works. The Laplace transform is analytic in the right half lambda plane. This is lambda. And so the typical thing to do is to take a path that looks like that, going from minus I infinity to plus I infinity, and in the region of analyticity. And there's a Fourier type integral that gives you the inverse Laplace transform. And if you do that to this formula that I didn't show you in detail, you get a mess. It really is a mess. Not only is it a mess, but there seems to be very little you can do with it. So we were about to give up on this approach. And then one remembers elementary things like Cochise Theorem. You can deform this contour. You're in a region of analyticity. It won't change the integral at all. So you can change the contour. Okay, I don't tell you how to do it, but there is a changed contour, gives you the same answer. And in that changed contour, it becomes very pleasant. Okay, so let me show you the formula. So U is the inverse Laplace transform of the Laplace transform. And there's the formula. So actually, it's the real part of H that's really the thing we're after. So okay, you perhaps if your eye is not into these things, you'll look at that and think he thinks that's nice. Compared to what? But in fact, it is nice because you see all these e to the I mu cubed t's here, 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 and there's even a better term there. That's the smoothing. That's the Korteweg-de Vries smoothing. And that's exactly where the smoothing comes from for Korteweg-de Vries. So you now can go to work and use the tools that the harmonic analysts have built and analyze those four terms and discover that, sure enough, there is smoothing. And it's quite interesting. There's a smoothing in terms of the spatial structure and the temporal structure. And I don't want to dwell on this, but there are things called Strickart estimates that follow from that messy formula. And with those Strickart estimates, you can then bring home a well-posedness theory. So let me, for some reason I put the names at the end instead of the beginning. So what we have is that problem that I'm interested in is locally well-posed this may look a little odd, but it's the right relationship between space and time. So the initial data is coming out of HS of R plus, and the boundary data is coming out of HS plus 1 over 3, and that should be loc because it doesn't need to decay as t goes to infinity. HS plus 1 over 3, that's the natural balance between space and time in this problem for any s bigger than minus a half. Okay, and it's global provided s is bigger than or equal to 1. So, okay, you have a very nice theory for that. Plenty for the problem. Now, in a certain sense, these existence, uniqueness, continuous dependence results that we all prove, me too, are not very scientifically interesting. What would be interesting is if it wasn't true. In other words, if you had a problem that a mechanician or a physicist was using and it wasn't well posed in some space that they would agree is interesting, that is interesting. But just to tell them that it has solutions and they depend continuously on everything in sight, they'll sort of say, yes, we know that. So I have two minds about these things. However, that wonderful formula I showed you a moment ago has buried in it more information. So let me show you some information it has. There's a property that I'm going to call asymptotic periodicity. This is a situation exactly like in my channel experiment, where I start with zero initial data, and I have boundary data, which is periodic of some period. It doesn't have to be periodic everywhere. It can be asymptotically periodic, but let's have it periodic. Okay, so I have my channel, and I'm oscillating this thing periodically. Okay, now what will happen? What does one, well, you're going to generate waves, of course, but I mean, can you say anything about them? And the answer is you bet. It turns out that they are eventually, at every point x, each individual point, if you look at it as a function of time, it will settle down and be periodic of the same period, asymptotically. And in fact, not only does it happen asymptotically, it happens pretty quickly. Okay, is that in fact what one sees? That's an interesting question. So let me go back now to this experiment. So here we are with the experiment. Okay, remember what I'm doing. And now I'm saying that this is periodic, which is in fact exactly what we did. So here is that's boundary data. That's a typical boundary data. Quite periodic, as you see. It's more or less a sine wave, but it doesn't matter what it is. I'll put that data directly into a numerical scheme for the evolution equation. All right, and let's just have a look at what happens. So now I'm going to show you what happens down the channel. So these are at the other three measuring devices. This is the next one after the first one is here, and it gave us data. Here's the next one, next one, next one. You see the wave arriving later. And you see that, indeed, the thing very quickly at each point settles down and becomes periodic. Now, this is for a nearly linear wave. If you move to a nonlinear wave, well, this is actually the kind of wave that you're interested in for the nearshore zone dynamics that I'll talk about in a second. You see that it is still periodic at each point of the period that you foreset, but the structure of it changes as you move down the channel. This is something that Stokes understood in the 1840s, not at this level. And by the way, you see comparison between experiment and the theory. The line is the piecewise linear interpolation of the output of the numerical scheme, and the little diamonds are the data. Just to give you an idea that the wave that we're talking about is not so simple, that's what the computer generates. That's what the computer thinks is in the channel. Those are spatial traces at different times. But they're fairly complicated, as you see up here. Oh, sorry, that's not the right one. I beg your pardon. Here's the right one. That was for that almost linear wave. This is the one for the more nonlinear wave. You see, that's quite a complicated signal that one is generating in the channel spatially. Okay, so as I said, and which you can guess from also from the pictures I just showed you, there's a very good theory for this. Numerical schemes are not hard to build because it is a well-posed problem. It's not a problem that's difficult to handle. Now let me move to the second part of my talk, which is, okay, so more people. They're all in red, but they're not all my students. Some of them are. So the problem now I want to look at now is related to the one we just looked at, but of course it's much more complicated because it's a real problem. It's not a toy problem that we can sharpen our teeth on. So here's the issue. I have that's the bottom of the ocean. Here's the water. And I guess here you are, standing on the beach. Okay, this is the situation that I'm interested in. What I'm going to focus on are the structures, sandbars, that you find, not always, but sometimes in the nearshore zone. And the question I want to ask is, what generates them, and what maintains them, and what are their dynamics like? Okay, so that's the issue. It's a sort of a fundamental question you'd like to know the answer to. It also has some practical implications. All right, so what you do is you go, now you see why I did the experiment. I needed to know if I had a decent model for surface waves. Now, of course, this is not a flat bottom. It's not like my experiment. In fact, of course, I'm only going to be concerned with a region here where, so there's going to be waves coming in from deep water. Here's where I'm going to model things. I will forget about what happens here, And on a very gently sloping beach, there's actually very little energy coming back because most of it gets lost in the braking and the run-up and the swash. On more steeply sloping beaches, that's not true, and then you have to use a more complicated model, which I won't go into today. All right, so now the model becomes, it's still the Korteweg de Vries type model, but now you're going to see the physics. There's a coefficient, well, in the flat case, it was just GH, where H was the depth, but now H is a function of X. X is still the variable going into the shore. And then there's other terms here. There's the eta X term also has a coefficient which depends on H, and the eta 3X terms likewise has a coefficient which depends on H. Okay, the details are not important. It's a Korteweg de Vries type equation, but now it's variable coefficient. Okay, now none of that, this kind of situation, none of that bothers us. So long as H doesn't get too small, the theory works perfectly well. It's just not as pretty and not as complete. But nevertheless, one can make a theory. And then, but okay, that's just for the surface. We haven't talked about moving the sediment yet. So how do we move the sediment? Well, so our idea was the following. You have waves coming in, which you can predict to some accuracy using an equation like this. Now, as soon as you have predicted the surface elevation, at each time, remember how it goes in waterways, there's a velocity potential in the bulk of the fluid if you ignore viscosity. So I ignore viscosity for a moment. Okay, so we want to solve Laplace's equation in a known domain because I now know where the boundary is. See, I'm not in the situation, if it was the Euler equation, we would need to predict the boundary as well, but I now know the boundary. So this is not hard. At the level that we're working, you can actually more or less write it down. So you can then take the gradient of that. That is the velocity field in the bulk of the fluid. Okay, so you now know, to some approximation, the velocity field in the bulk of the fluid. Okay, now, I'm assuming it's inviscid. That's a good assumption for waves in the bulk of the fluid, but not near the bottom. Near the bottom, you can't get around it. There's a boundary layer down there, a lot of damping. Especially there's a lot of damping when it's a sandy bottom. So now let's blow up the bottom a little bit. So here, and let me pretend that there's a viscous boundary layer that you can actually see. So now what do I know at this point? I know the velocity field, I've predicted it, above this boundary layer. So now I can think to myself, okay, this is a viscous boundary layer driven by a known velocity field. That's a problem. It's an interesting fluid mechanics problem, which was actually solved, some level of approximation, by Michael Longet-Higgins in his PhD thesis, turns out. So we used Longet-Higgins theory, and from that theory we can predict the velocity field in the boundary layer. Okay, we don't actually need the vertical one. It's just the horizontal one we need. Okay, and of course it goes to 0 at the boundary. Okay, and now, let me call it capital U for a second. Capital U of x, y is the vertical direction, and t. This is all two-dimensional, by the way. I'm not talking about longshore variation. We have this function. We now know that. And so what you do is of course, you don't care about the back and forth of the sediment transport. That's not interesting. It's only the bulk transport that you care about. So you multiply it by a density that's a function of y, and there's theory of various sorts to say what that might be. And actually, I'm sweeping a lot of things under the carpet here. You integrate it over the boundary layer, because I actually don't care much about the details of it. It's only the bulk transport. And then you integrate it over the period. So I guess I need a dt here. Well, okay, it's not really that. It's, let's say, t plus t to t plus t. Integrate over one period. And again, I'm thinking of periodic motion coming in. Okay, that is what Stokes would have called the mass transport. Okay, so think what's happening in the fluid. Particles are here, and they each time a wave goes by, they make a little movement. They're not right. Just stand in the water and you'll feel what's going on. If the theory is linear, it closes. But if it's nonlinear, it doesn't close in one period. And that's where the transport comes from. Okay? So it could be either way. It could be forward or backwards. Oh, thank you. It could be forward or backwards. But anyway, that's where the transport comes from. And all of this, which I'm not going to write down in any detail, allows you to predict, we call it Q of x and t, the mass transport. And now there's some physics here. You have to identify the sediment transport with some function of this thing. And there's theory for how you do that, which I won't go into. Once you finish that, there's a conservation law. dh d tau equals d by dx. Well, it's not exactly q, but let me pretend it's q. This is q of x and t, but remember, it depends on eta and h as well. Well, this conservation law is just conservation of mass. That's all it is. On the bottom, it just says you can't create or destroy sand. And so now you have the whole model. It's this evolution equation coupled with this conservation law, coupled through the process that I just outlined. Okay, so there's nothing simple about that. I mean, it really isn't simple. I don't want to. I could flash up some formulas that look impressive, but I won't do that. Now let me show you. Let's see if it works. Does this kind of thing actually work? Well, okay, so we did some other experiments. It's a different experiment. It's a different wave tank. This is a big, huge engineering type wave tank that sits in Gdańsk, 26 meters long, with a ropey motor driving the paddle. So you turn the paddle on and you let it go. And it's kind of periodic. The motor's about like the motor on your washing machine. So not a very good one. What I'm showing you here is the results of 4 different experiments. These are the final states. So what happens is the sediment starts moving around as soon as you turn it on. Complicated things happen. As the bottom deforms, each individual wave sees a different situation. So the surface wave situation deforms, and there's an interaction, a nonlinear interaction between these two. It's 2 free surfaces here, but with very different time scales. But eventually, at least in the experiments, it settles down, and you reach a macroscopic steady state. Now, it's not microscopic. Microscopically, it's always the case that sediment's coming up and settling back out. So there's a lot of stuff still going on in the boundary layer, but macroscopically it quits changing. Okay, those are the sandbars. Okay, so our model, that one that I just sketched, does generate sandbars. Let me show you a typical kind of situation. So focus on the bottom here. This is more or less the same as the experiment I just showed you. And you see that the bottom begins to deform. And it doesn't settle down right away. But it does eventually settle down. This is over a flat bottom and become periodic, in fact. Okay, but in general, it won't be periodic. So the model, and we have a whole range of things here, but that we've done numerical experiments. But let me finish now with the recent applications of this. All right, so another set of people. Oh, it's the same set of people. Sorry. All right, so what I'm going to show you is a test of the model, the best test we've been able to make, because you need data. Somebody's got to have data for you. What does this model need to initiate? I need an initial bottom profile, and I need to know what's coming in from deep water. Okay, now, maybe the initial bottom profile you might believe, but who's standing out there measuring the waves in deep water? I didn't see anybody here doing that. Not many places are there, but there are some, and here's one of them. So this is North Carolina. This is the Outer Banks. This is Kitty Hawk, where the Wright brothers flew their airplane. And north of there is Duck, which is another little settlement. Now at Duck, the U.S. Army Corps of Engineers, along with a bunch of oceanographers, have been for 20 years. They've been there 20 years. And this is the local situation. They have a kilometer of beach, about a kilometer of beach. They've got a 600-meter pier that runs out into the water. They've got arrays of instruments. that are mounted continuously, video towers. Every once in a while, they put new instruments in to do some particular set of measurements. They're measuring the wind, the waves. Every month, they measure the bottom, once a month. Okay, so here's and it's the bottom I care about. Here's typical measurement. And there you see the entire data set that they generated. I'm going to focus on, in their little coordinate system, number 62. Remember, my model is one-dimensional right now, or two-dimensional. The reason I'm focusing on that one is I want to stay away from the pier, which messes up the waves in a way that we don't care about, because there aren't all that many piers. Well, maybe you would care about it, but we didn't care about it. Okay, so now at location 62, let me show you the data. There it is. It just looks like a cloud of points. That data would cost several $1 million. Many millions, several tens of millions of dollars. So that data is enough to generate what we call an equilibrium beach profile. And there you have it in the solid blue line. And we have some theory for that, which I won't go into. But that doesn't tell the story at all. That picture doesn't tell the story. Here's a typical measurement. This is an 83. And you see that there's 2 bars there, 2 sandbars. And you often see 2 sandbars. So a whole range of times you see 2 bars located about at 200 and 400 meters in their local coordinate system. And 0 is not the water line. Okay. So I know I'm supposed to finish on time, so I'm working at it. At other times, you have 1 bar. Okay, that's 81. And that also is something you see now and then. Okay, the oceanographers call the 1-bar configurations anomalous because, well, they're just like us. Things they don't understand, they give bad names to. We do the same thing. We looked into the data set and found a transition. So there it is. You see in 89, there's a 1-bar configuration in January and February, and in March, there's a 2-bar configuration. Okay, now remember, they're measuring everything in sight. So that's the kind of data you get to work with. A little bit noisy. You need to filter that to get anything out of it. In that period where the transition occurred, here, the wave height, focus on that. There was a huge storm that came through. Now, the energy is proportional to the square of this. So this is really quite a large storm that came through. And they have measurements and so forth. So one can, I'll just show you a picture and you'll see, get the idea. You can determine the kind of parameters that we need in our model to some approximation. Remember, this really is very ropey. But okay, we're doing the best we can. Okay, so now we put that into the model. We calibrated it for time, and then we put it into the model. We started with the 2-bar configuration. So time is running this way. It was a 2-day storm, and in fact, that's what we calculated. And you see the single bar, here's the side view, moving smoothly over into 2 bars under the different wave environment. So we got excited about that. I mean, we really were. We didn't expect to do so well. Let's put it that way. So we now got ambitious. There's the whole data set for where the bars are, 20 years worth of $30 million. You see a lot of variation here. A lot of that is just seasonal. We think we understand that. But I can make it look simpler by putting big black lines. Okay, now you have something you might try to predict with this model. You've got a 2-bar configuration at 200, 400 here. There's a 1-bar at 220, 1-bar at 320, back to 220. Okay. Could our model account for what you see? Okay, so let me quickly show you. The answer is yes, or I wouldn't be up here telling you about it. So the red profile there at the bottom was that equilibrium beach profile. We had to have a starting point, so we just took the equilibrium beach profile. And then we looked in the record to see what happens. In this period of time, so this is 84 to 88, typical thing that happened, most waves don't matter, by the way. These bars lie at 6, 8 meters deep. So the wave doesn't penetrate unless it's big. So it's only the storms you care about in this environment. That's not true of all beaches, but in this beach, it's just the storms. So you can check the storms. And sure enough, in this period, a typical winter, there were no storms in the summer. Typical winter was 3 to 5 storms, and they all had the same characteristic. So we took those characteristics as the input data for our model. Now, I want to emphasize there's no free parameters here. We're not doing data fitting. And we generated, as you see, a pair of bars. That's what the model predicted. And sure enough, that's quite close. Sorry, wrong slide. There it is. That's quite close. The black is what we predict, and the little dots are the actual data in that period from 84 to 88. And so we got those bars pretty much right. Now, what happened to... Okay, so remember the... Okay, I won't go through all of this. What happened that went from 2 bars to 1 bar? Well, we're just looking in the data set, and it turns out that there was a year, 88, where there were no big storms. There were small storms, a bunch of small storms, but no large storms. But what that means is the wave amplitude is smaller and the period is different. And that's all you need to get our model going. So here's what we predicted. Yeah, here, let me show you So the red, again, is the initial profile. It's the 2-bar configuration from the last calculation. And the blue is the final profile with these new parameters in the model. And you see that the agreement's really quite good. Okay, well, this one's always interesting to look at. All right, so I'll finish with this one. Here you are at 220, and then the next year it's at 320. Now it's 100 meters. You've moved a lot of sand 100 meters. I mean, it really is a vast amount of work to move that. I mean, just think about doing it with a shovel, right? You wouldn't do it. Well, it's underwater. So what we looked in the record to see what happened, and what happened was a hurricane came through. So this generated several things. First of all, the mean water level rose a meter. That's what happens in hurricanes. The wave amplitude went up by a factor of 2 or 3, and the period was 20 seconds. 20-second waves are pretty long waves. Okay, so we just put that in the model. The red, again, is the initial profile. It's that 1 bar from the previous calculation. And we put in the hurricane, our version of a hurricane. And the black, again, is what we predict. And the data is there for you to see. So again, we're getting this. We were impressed with how well we were doing. I mean, as I say, this is the best data set in the world for this kind of thing. So my collaborator, Karakevich, has taken her show on the road, and she's now working on beaches all around the world using this model. So she's worked in Australia. She's in Tunisia right now. Where is she? She's in Jerba. Well, the Tunisian coast is a tourist coast. Beautiful coast, absolutely gorgeous. There's a site here that's about 8 or 9 kilometers of beach, which is prime territory for tourists, and it's going away. They're losing their beach. So, well, they're not happy about that. So she is a consultant on that. Let me show you a sort of a big picture of the beach. This part's undeveloped, but that's the kind of beach you're talking about. Huge, wide, wonderful beach. But if you look a little more closely, you'll see that there's a lot of places where there's no sand. That's not good. And in fact, let's see, I had a picture of one of their fancy hotels, which has been invaded by the loss of sand, and the deck is collapsed at this point. Okay, I don't seem to see that picture. Anyway, so they have a real problem, and they've called her in. I'm involved in a peripheral way. We've been making measurements, they've been making measurements in this pilot part of the beach. And it's the same kind of data that I showed you before, only we've only got 1 year of it now, not 20 years. So this is the kind of data you get to work with. And the first thing we wanted to do was see if the model could predict more or less what we had measured. So there's what we measured. Now the black line is just the equilibrium profile. That's not a prediction. So there's a couple of bars in this situation. There's one here, and there's one here, sometimes two. Okay, so we simulated that with the record that we had. So now these things aren't years, these are months or something like that. And you see that the simulation's in dark blue. We have predicted bars in the right place. So now using this model, we went to work. See, that what's going on here is that the beach is being washed away. The question is, what do you do about it? Well, one solution would be to build a heavy structure out in the water to keep the waves off, to get the wave energy down. That's very ugly. And it doesn't always stay put. A lot of times they go away. And it's incredibly expensive. I mean, incredibly expensive. So we have another method, which is also expensive, not as expensive. And that is to throw sand in the water where those bars are. In other words, nourish the bars. This is a method which has worked in Australia. And there was a piece of the Gold Coast that lost its beach. And Karakevich told them where to put sand. And the waves generated a bar which wasn't there, and then that bar protected the beach, and they could nourish the beach, and it's been there for 10 years. So her scheme now is to nourish these bars exactly where you see the red arrows. So she, as I say, she's in Tunisia right now trying to sell this scheme to the Tunisians. So this is millions of dollars. Imagine a boat out in the water pouring sand in the water. Right? That's what happens. Okay, I apologize for going on. It's time for pictures. Thank you for your attention.
Are there any questions or comments?
I have a question concerning your first part.
Yes.
The criteria
Yes.
of forced periodic regimes.
Yes.
Is it possible to describe asymptotic regime like just extendable in both directions such that it will be periodic in given point? That's your final result.
The final result was that it becomes periodic at each point. That's right. And there's more to it than I told you, in fact. There is a solution. There's a solution of the... Okay, so this is x and this is t. There is a solution which is time periodic, which is kind of the limit of the forcing. So forget about forcing now and just have, well, don't forget about it, but have a given periodic forcing here. There is a solution of x and t which is periodic.
Yes, here, and it is your limit.
Yeah, it's the limit. You're exactly right.
I think it's possible to describe it in terms of inverse spectral data. Yes,
Well,
this I don't remember that.
See,
anybody describe it?
No, nobody's done that. And in fact, the inverse scattering theory applied to boundary value problems is still in its infancy. So the only people who've done work that makes much progress at all are Sung and Focas, as far as I know. So they have actually, at my suggestion, they have tackled this problem with the inverse scattering theory. Yeah, right. And they have a theory for the Schrodinger equation, which is not too bad. But for Korteweg de Vries, okay, time. We're being told to go get our picture taken.
Well, thank you, Jerry.